Hey guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In our discussion today, I'm going to look at an element of elastic potential. And in our last discussion, I had basically mentioned that we can try to define this aspect of potential energy in terms of gravitational potential and elastic potential. Now, in this particular case, we are given a few examples of these two specific product categories of elastic or other potential energy. And in this case, we're going to look at elastic potential and find a way in the last bit of our discussion on how we can represent this aspect of elastic potential. Now, in this case, I'm going to borrow from previous discussion we have had on particularly trying to derive the concept of work done in trying to stretch or compress a spring. And in this case, they said that basically for us to find the work done, we're going to consider a force which is applied. And of course, this is going to be in combination with the distance which this specific force is going to move an object. Now, in this case, I'm going to use this specific illustration for force and distance, and particularly work. I'm going to use W in this specific case. So in a sense, we developed this specific expression for work, but we had mentioned basically that we can have this force which is applied given in terms of a negative kx, where I had said that this specific k is going to, x is going to imply the distance over which this spring is going to be stretched. And then we're going to consider k as a spring constant, which we are going to see being mentioned particularly in our subsequent videos. Now, in this case, we're going to consider the energy which is going to be, of course, achieved in this case, perhaps through the process of stretching, whereby I'm going to use this first illustration and the second one in trying to consider this specific case of elastic potential. Now, in this case, if of course, we can consider the first figure, which is going to be A. This is going to be a mass that has been attached to a particular spring, and therefore the resulting effect is going to be a stretch of this specific mass by a particular distance. Now, when this particular force is going to be attached, we are going to see that there's going to be some energy which is going to be stored in this specific spring. Now, the energy which is stored is equivalent to the work done in trying to stretch this spring from its initial position. Now, in this case, then therefore we shall have the energy stored equivalent to E, which is basically the energy, and therefore I've said that this energy is going to be equivalent to the work done in trying to stretch this spring. Now, we can analyze this specific, of course, a concept of work, and in us finding this work, then therefore this work is going to be equivalent to the elastic potential of this specific spring. Now, we had said that we can consider an element of work given in terms of dW, and this, of course, is going to be a resultant of the force distance, the force times the, of course, a segment of a distance which has been stretched by this small element of work. Now, in this case, for us to find the total work done, we're going to do an integration over these small elements of work, and of course, the total force times the elements of a distance, which the summation of the elements of a distance which have been, of course, achieved. And therefore, the total work done by the spring can be given in terms of dW is equivalent to the negative, the integral over this specific function over kx dx, given as such. Now, for us to find the total work in terms of W, then therefore, this is going to be given in terms of a negative, the integral over this specific kx, and then we're going to have a dx from the initial position, which we are going to use as x initial, to the final position given as x sub f given as such. So in this case, for us to perform our normal integration, we're going to have the constant of k brought out of this integral sign, and then we're going to have kx and k final given as such dx, and this is going to be equivalent to work. So this is going to give us an integral of a particular form, whereby we're going to see that basically this is going to be negative k, and then we shall have this element of the square of x of all over 2, and then we are going to be having from x initial to x final given as such. So this is going to follow the procedure of performing our normal integration, and therefore in this case we're going to see that in us to considering this a small aspect of a negative sign, we're going to perform an evaluation and our work is given in terms of a half k, of course, and we're going to see that these two specific position for the initial and the final are going to appear as such, and therefore that's going to form a element of work. So finally, this is going to yield an equation of the form work is equivalent to energy. And this, of course, is what basically mentioned at this specific section of our discussion. So we're going to have it represented in terms of this specific representation, whereby, so basically I can rearrange this one and have it as half kx squared given as such. So in this case, we're going to see that in stretching the spring from its initial position due to application of force to the final one, we're going to use to find that this specific work done on the spring can be given as an integral part of this specific evaluation which I have done. And the elastic potential, which I said in this particular case, is going to be given as the work done in stretching this specific spring. Now, in this case, we're going to consider the initial and the final coordinates for this specific representation for xi and xf, xi and xf in terms of an equilibrium position of x is equivalent to 0. Now, in this case, in order for us to evaluate this second one and quantify this specific force or the work done, we're going to see that this x is going to stretch from 0 to 20 meters. And of course, we're going to consider the second one as well from the equilibrium position of 0 to 40 meters in that particular case. Now, therefore, we are going to see that the elastic potential can be given, or the elastic potential function can be given in terms of this specific representation. And this is going to be applied for any closed system, as we're going to see. Therefore, we can have this specific formula for our final representation of the elastic potential or elastic or the elastic potential function for any closed system given in terms of Vs sub s is given as a half kx squared, which is basically the work done in trying to stretch this spring. Now we're going to have an application of this specific equation in trying to do an evaluation, which is going to form a final bit of this specific discussion. Now assume that we have, presume that we have understood how we can find the elastic potential of this specific kind of a system, and therefore we're going to consider this specific final case for our evaluation. Now, if we are requested to find the elastic potential or the work done in stretching this spring from its initial position of 20 meters to 40 meters by hanging this specific mass, then therefore we are going to consider this equation, and then we are going to have this one. So if we are given the elastic, rather the spring constant in terms of 40 newtons per meter, then we can evaluate the work done, which is given in terms of a half kx squared, which is similar to the elastic potential, which is equivalent to a half times 40 newtons per meter times the square of the distance. So this is going to be, as we said, the value over x initial minus x final given as such. And the difference between this one, of course, we're going to find an absolute value of 20. So therefore, this is going to be a half times 40 newtons per meter times 20 meters. So in this case, we are said that this is going to be basically a square of this specific distance, and therefore we expect to have a square of a meter given as such. So this is going to be given in terms of work is equivalent to, so this is going to be 20, this is specific point, implying this is 20 newtons per meter times 20 meters times 20 meters. So I'd like to do an evaluation for these specific units, and therefore we're going to have this one given in terms of 8,000 Newton meters. So in this case, we are going to conform with the standard units of applying this specific aspect of our work. And of course, this is going to be equivalent to joules, as we have been discussing from our previous discussion. So basically, we're going to use other, of course, conversion units which we are going to come across. And therefore, I request our members to kindly check our description boxes for various links of other videos which we have done in terms of perhaps work potential energy and of course kinetic energy, and that is going to give us an essence of what basically this concept of work is. So I'd like to request our members also to kindly subscribe, engage us in the comment section, and also ring that notification bell for other videos in sciences and mathematics. So that is it for now, guys. Bye, God bless you. Catch us in our next video.